Good day. I hope you're all doing well right now. Today, we will talk about chain rule when dealing with functions involving several variables. This topic will be divided into two parts. For this video, we will tackle simple cases of how to apply chain rule. We will deal with the more complicated cases on the second part of this topic. This concept is not new to us. We've already encountered this in Math 21. Let's recall how it works, shall we? We have y that is a function of x, but x is dependent on another variable t. Note that the functions we're dealing with are all differentiable for this concept to work. Then, y is also dependent on t, and we can get the derivative of y with respect to t using this formula. First, we get the derivative of y with respect to x, and then we multiply that with the derivative of x with respect to t. Easy, right? The question now is, how do we extend this concept when we have functions of several variables? We first tackle the case when the variable z is dependent on two variables, x and y. To keep this simple, suppose that x and y are dependent on only one variable, say t. Again, these functions must all be differentiable. Hence, z is a function of t, and we can get the derivative of z with respect to t using this formula. Let me give you a few moments to look closely at the formula. If you need more time, pause this video now. Don't be intimidated with this formula. There's an easy way for you to remember this. We need to draw what we will call the tree of dependency. Let's start with z. It is dependent on x and y, so we draw through two branches below z. One is connected to x, and the other one is connected to y. Now, x and y are both dependent on t. So we draw one branch under x and another branch under y. We write t under x and t under y. We are allowed to write t several times. We can now imagine that each line on this tree will represent the derivative of the variable on top with respect to the variable at the bottom. So for example, this line here represents the partial of z with respect to x. And this line here represents a derivative of x with respect to t. This one represents a partial of z with respect to y. And this one is a derivative of y with respect to t. Now, why are some of these partial derivatives while the others are just your usual derivatives? Remember that the usual derivative are for functions involving only one variable. So that's why there's a derivative of x with respect to t here, and there's a derivative of y with respect to t here. Now, partial derivatives are for functions of several variables. That's why we have partial derivatives here and here. Finally, the formula for the chain rule considers all of the paths that start from z and end in t. So we have this path over here and another path over here. So when we write the chain rule for the derivative of z with respect to t, it is now the partial of z with respect to x multiplied with the derivative of x with respect to t. And then we add that to the partial of z with respect to y times the derivative of y with respect to t. Let's look at an example, shall we? Let z equals x squared y, where x equals t squared and y equals t cubed. Use the chain rule to find the derivative of z with respect to t. So recall our formula for the chain rule over here. Now, we take the partial of z with respect to x. In this case, that's 2xy. We multiply that with the derivative of x with respect to t. In this case, equal to t squared. 2t. Then plus the partial of z with respect to y, which is x squared, times the derivative of y with respect to t, which is 3t squared. When we simplify this expression, what we will do is to replace the x's by t squared and the y's by t cubed. So upon doing that, 2xy will now become 2t to the fifth, and x squared will now become t to the fourth. After simplifying this expression, we will get 7t to the sixth. Now, alternatively, we could just have replaced by t squared and y by t cubed in this expression here. So after doing that, so x squared will now become t squared quantity squared times y, which is t cubed. When we simplify this expression, we will get t to the 7th. And of course, it's now easy to get the derivative of this expression, which is 7t to the 6th. This is the answer that we obtained using chain rule earlier. So the question is, why do we need to use chain rule in the first place? This is an easier solution, obviously. But remember that there are certain examples where the chain rule method will be easier, especially with dealing with other functions like the exponential or the trigonometric and so on. Now, let's make things more complicated. We still have z that depends on the variables x and y. But this time, suppose that x and y depend on two other variables, s and t. Previously, x and y depend only on one variable. And again, we want these functions to be differentiable for the concept to work. Then, z is also a differentiable function of s and t. This allows us to get the partial of z with respect to s and the partial of z with respect to t. How? Let's draw the tree of dependency again. So we have z dependent on x and y. That's why we have two branches here. But this time, x and y are dependent on two other variables. So that's why we have two branches, s and t here, and also two branches here, s and t. Now, to formulate the partial of z with respect to s, again, we consider all of the paths starting from z and end in s. So that's the path here and the path here. So to formulate the partial derivative of z with respect to s, that's the partial of z with respect to x multiplied with the partial of x with respect to s, and then add that to the partial of z with respect to y times the partial of y with respect to s. So that's a formula for the partial of z with respect to s. Similarly, to formulate the partial of z with respect to t, we again consider the paths that start from z and this time end in t. So we have this path here and this path here. So this will become the partial of z with respect to x multiplied with the partial of x with respect to t plus the partial of z with respect to y times the partial of y with respect to t. So let me give you now some time to look at these equations. If you need more time, pause this video now. To illustrate, let's answer this problem. We have z is equal to e to the xy, where x is equal to 2s plus t, and y is equal to s over t. Find the partial of z with respect to s and the partial of z with respect to t using chain rule. Assume that s is equal to -1 and t is equal to 1. So based on the formula for the chain rule, the partial of z with respect to s is equal to the partial of z with respect to x. In this case, it's y e to the xy. We multiply that to the partial of x with respect to s, which is 2. Then add the partial of z with respect to y. In this case, it's x e to the xy, multiplied with the partial of y with respect to s, which is 1 over t. Notice that we have a common factor here, e to the xy, so we factor it out and write it like this. Similarly, we have the partial of z with respect to t, which is equal to the partial of z with respect to x, which is y e to the xy, multiplied with the partial of x with respect to t, which is 1, plus the partial of z with respect to y, which is x e to the y, times the partial of y with respect to t, which is -s over t squared. Again, here we have a common factor e to the xy, so we factor it out and write it like this. Note that when s is equal to -1 and t is equal to 1, we solve for the corresponding x and y using the expressions that we have here on top. So when we replace s by -1 and t be equal to 1, we will get x is equal to -1 and y equal to -1. So now we will replace all of the x's here by -1, all of the y's again by -1, all of the s's by -1, and all of the t's by 1. So we will get the partial of z with respect to s is equal to e to the -1 times -1 times 2 times -1 plus -1 over 1. Upon simplification, this is equal to 3e. We do the same thing for the partial of z with respect to t. So that's e to the -1 times -1 multiplied with -1 minus -1 times -1 over 1 squared. And after simplifying, we get -2e. This ends part 1 of lecture 1.5. We will continue with more complicated versions of chain rule in part 2 of this lecture. See you then!